This is the Cherry Pick channel and we're talking about data science. In this video, you will learn how to configure the Optimizely calculator for A/B testing. Link to the calculator in the description.
The Optimizely sample size calculator helps you estimate the number of visitors you will need for a given experiment. In traditional A/B testing methodology, we were required to calculate the sample size before running an experiment to know when we are allowed to first look at the results. Optimizely Stats Engine removed the need to do so before every test, but the sample size calculator can still be valuable for us while planning an experiment and while it is already running. It enables us to get a better idea of whether we should expect to see a statistically significant result within a reasonable amount of time. The sample size calculator is available for everyone online, and it takes 3 parameters as input. On the very bottom, you have the statistical significance level you are working with. It should match the number you set in your project settings. This is unlikely to change much across experiments. The more interesting inputs for us are the following. Baseline conversion rate, which is the current conversion rate or whatever you are testing on. It usually can be calculated using data from your analytics platform or previous experiments. Then, we have the minimum detectable effect. Traditionally, you would be asked to guesstimate what kind of effect you should expect to be able to measure. That means that if we expect our experiment to drive no less than 5% improvement or drop, then we would plug the numbers and get an answer for how many visitors per variation do we need to test in order to be able to detect in a statistically significant way an effect of 5% or more over our baseline. If we are running a classic A/B test with one original version and one variation, then the total sample size would be that number times 2. The basic relationship here is the lower the baseline or the minimum detectable effect are, the higher the sample size per variation. The problem with the traditional approach is that we were being asked to estimate the effect of a test we are running, whereas the very reason that we are testing is because we do not know what kind of effect this experiment might drive. That was one of the motivations to build our stats engine, which strips this need away from the tester. So how can we better utilize the sample size calculator in order to inform our decisions? The first use case would be when we are planning to run an experiment. We can use the sample size calculator to see how many visitors we will need to test on to be able to detect a certain result, and vice versa. We can use what we know about the traffic to the area where we are experimenting on in order to see what kind of effect we will be able to detect in a reasonable time. For example, imagine we are planning an experiment based on the following hypothesis. Because of data from recent usability research, we believe that if we move our newsletter sign-up call to action above the fold, we will increase clicks on the sign-up button. We would like to understand whether this experiment makes sense to run and what to expect. Let's try to plug the numbers in. First, we are working with a 90% statistical significance threshold, so we will leave that as is. Then, after looking at our analytics over the last 3 months, we see that our baseline conversion rate is 7%. Now for the more difficult part, the minimum detectable effect. If we knew how much of a difference we should expect, for example 10%, then we would have to type this into the calculator and see how many visitors per variation do we need to detect that difference. Instead, let's look at it from the other direction. Let's see how many visitors we have to that page per week to test on. Let's say that by looking at our analytics, we estimate about 20,000 visitors per week. That means that if we would run this experiment for 4 weeks, we have about 80,000 visitors to test on, and we have 2 variations, A plus B. So whatever the calculator shows us, we multiply by 2. Now we can ask the question, what kind of minimum effect can we detect? To estimate that, let's play around with the minimum detectable effect until the sample size per variation times 2 is just under or equals to the total amount of visitors that we have for this test, which we previously calculated. The answer, after a bit of playing with the calculator, is 7.3. This means that if the variation will beat or lose to the original by 7.3 or more, then 4 weeks from now, we will be able to detect that in a statistically significant way. If it beats the original by 5%, for example, then we will need to run the test longer to get a reliable answer. After playing with the numbers a bit, we can get a better idea of how long it will take to observe a reasonable range of effects and whether this time frame is okay for us. In some cases, we might be limited in the time or traffic we are willing to invest in this test. Then we can use the calculator to see what kind of effect can we detect within that time frame and whether it makes sense for us to test this. So if for whatever reason we only have a maximum of 6 weeks to run this test, which means 60,000 visitors per variation and 120,000 in total, then we see the minimum detectable effect is 6%. We now need to ask ourselves, are we confident that the change that we are testing is meaningful enough to generate a minimum of 6% uplift or drop? There is no clear-cut answer here, but at least now we have some data to help us decide whether to go ahead with this experiment or invest the time and resources to test something else. The other use case for this calculator is while a test is running, and we would like to know how long it would take in order to reach statistical significance. Because of the dynamic nature of the stats engine, we do not ask you to calculate anything before the experiment. But what if the test has been already running for 4 weeks and we do not have a statistically significant answer? How much longer do we need to wait in order to get a reliable result? In this case, we already have the baseline conversion rate and the improvement in the results page, and all we need to do is plug them into the calculator. Now we can clearly see how many more visitors do we need to get a statistically significant answer. One thing to keep in mind is that it is only true if the variation conversion rate and the improvement remain the same over time. If there is a high fluctuation in the conversion rate, the statistical significance will be reset, and you will need to wait for it to stabilize again in order to make these calculations. So, if the calculations are telling you that you should have reached statistical significance by now, then your conversion rate is probably fluctuating too much. Let's look at an example. Let's take the role of a big media company. We would like to measure social media shares for our content. After a week of running this test, we can see that one of the variations is winning, but the other one is still inconclusive. Should we wait for it to reach significance or stop the test and declare variation 2 the winner? If we take those numbers to the calculator, we see that in order to get a statistically significant answer for variation 2, provided that the conversion rate doesn't fluctuate, we need about 430,000 visitors per variation, which is a total of about 1.3 million visitors in total. With the current rate of visitors to the experiment, it will take over 2 months. Because social media shares is not a crucial goal as, for example, revenue, and since we already have a clear winner, I would recommend not to wait for statistical significance on variation 2 in this case. Unless, of course, social media shares are a very big priority right now and you are willing to invest the time to get a final answer. In our next example, we are looking at completed purchases for an e-commerce site where one variation is already losing. Our only hope for a winner here lies with variation 2, whose difference interval is lopsided towards the positive, but the results are still not statistically significant. Again, we plug the numbers into the calculator and it tells us that we need almost 1 million visitors per variation, 3 million in total, to get statistically significant results. This time, the rate in which users are coming to the experiment is about 35,000 per day, and it will take us just under 3 months to get an answer. Because of what we are measuring here is purchases, for which the uplift can potentially be up to 16%, I would say that it might be worth the time to see this experiment through. That is because a bump of even 2 or 3% in purchase rate is very big for a business, as opposed to a relatively minor metric like social shares from the previous example. So, to recap, before running an experiment, choose the goals that you are going to measure and take a quick look at the sample size calculator to see whether you have a good chance of reaching statistical significance on them. Then, while running an experiment, you can always plug the numbers into the calculator to get a better idea of how long this test should run to get statistically significant results. Both cases will enable you to make better decisions on whether to stop a given experiment or let it run, and whether you should run it in the first place. Thank you all for watching, and happy testing!